Good afternoon, everyone. My name is Alon Rosen. I'm the chair of the next session, the foundation session. Let us begin without further ado. So the first speaker is Miranda Christ. She will tell us about good things come to those who wait.
Thank you. So this is joint work with Joe Bonneau and Benedict Boontz, who are here, and Yuval Efron, who is not here, unfortunately. How do I advance the slides?
You can also point at the screen.
OK. So today I'll be talking about the fundamental problem of coin flipping. And in this problem, you have two parties, Alice and Bob, who want to agree on a shared random value. And of course, if Alice and Bob are together in person, this is very easy. They can just flip a coin. But we'll be considering the setting where they're not together in person. They can communicate only, say, online. And one attempt at building a coin flipping protocol might involve Alice sending over a random bit, Bob sending one as well, and then the output of the protocol is defined to be just the XOR of their two random bits. But the problem here is that if Bob is malicious, then after seeing Alice's random bit, he can choose his allegedly random bit to cause any output of his choice. So this is easily biasable by Bob. And one way we might try to fix this is by instead having Alice and Bob first commit to their random bits. And now, of course, Alice has to reveal her random bit. And we have a different problem now. Once Bob sees Alice's bit, he can't change what he committed to. But if he doesn't like what the output of the random protocol will be, then he can just pretend to go offline and prevent the protocol from ever terminating with a valid output. So the problem in both of these protocols is that Bob can see how his actions will affect the output of the protocol, and he can act accordingly to bias it or prevent an output. And Cleve showed in his seminal result that this problem is in fact inherent. So he defines a two-party coin flipping protocol as a protocol where honest parties always terminate by outputting some value, and the honest parties must always agree on the output as well. And he shows that for any such protocol, a dishonest party can cause a non-negligible bias. And here I stated it just for any two-party coin flipping protocol, but in fact, it extends to n parties as well. OK. And so despite this impossibility result, there's actually been a lot of work on coin flipping. And in this older, more theoretical work, people have tried to minimize the amount of bias in the protocol. So Cleve showed that there must be at least some bias, and so people will try to design protocols that come as close to this bound as possible. And in addition to this theoretical work, there's also been a newer line of blockchain-motivated work. So in the blockchain setting, coin flipping is very important for doing things such as leader election. And so there have been many blockchain protocols, which they call distributed randomness beacons, which just try to generate shared randomness. And interestingly, a lot of these blockchain protocols have negligible bias, even with a dishonest supermajority. So even if all but one of the parties are dishonest, still they achieve negligible bias. And this should seem weird, because it directly contradicts the impossibility result that I just showed you. And to show you sort of how this is possible, I'll quickly give an overview of one of these distributed randomness beacons. This is called Unicorn. And in this protocol, every party submits a randomness contribution. Then these contributions are combined using a random oracle. And then a function eval is computed on their combination, and it's passed through a random oracle yet again. And this is the output of the beacon. It's very simple. And it turns out that this protocol has negligible bias as long as any single user is honest. And the key here is this function that's evaluated on the shared random inputs. What's very important here is this eval function takes a long time to compute. So the contribution period is some bounded amount of time where people can choose their randomness contributions. And eval takes a much longer time than that to compute. So the idea is that parties can't tell how they would influence the output of the beacon when they choose their contributions. So eval is what's called a delay function. And the reason why this is secure is because nobody has time to compute the output of the delay function before choosing their randomness. And so prior work such as Unicorn has shown that you can use delay functions to construct dishonest majority randomness beacons. What we ask in this work is, what's the minimal object needed to circumvent Cleve's impossibility? So can we get away with something weaker than the delay functions used in existing work? And what we show is an equivalence between dishonest majority beacons and a certain notion of delay functions that I'll define for you later. And the way that we show this is by starting by assuming that we have a dishonest majority beacon, then opening up Cleve's proof to construct a weak delay function out of this protocol. And then once we have a weak delay function, we boost it to construct a strong delay function. And finally, we construct a dishonest majority beacon out of this delay function. And our protocol is essentially going to be the Unicorn protocol that I just showed you. OK, and so now I'll try to give a brief overview of each of the steps in our argument. The first is taking the dishonest majority protocol and using it to construct a weak delay function. And the notion of a delay function that we consider is slightly different from prior work, so I'll explain it for you. Our delay function consists of a setup algorithm that generates some public parameters, as well as a sample input algorithm that samples an input on which the evaluation should take a long time. And so this is in contrast to other delay functions such as VDFs, where typically the input is uniform. Ours might have to be from some specific distribution. And the properties that we want are efficiency. Eval should be polynomial time computable, though it should take a long time. So that's the second property, sequentiality, which says that no adversary that runs in too few sequential steps should be able to compute eval. And by this I mean they shouldn't be able to compute it except with negligible probability, but we also consider this weak notion of a delay function where the adversary just can't predict it extremely reliably. So there's some inverse polynomial probability on which it fails to predict the output. And to give you an example that you can think of, a heuristic delay function might involve taking some hash function and just evaluating it iteratively. OK, and so now we're going to open up Cleve's impossibility to actually construct a weak delay function from a coin flipping protocol. So the way that Cleve's argument goes is he takes a coin flipping protocol and he defines a bunch of different adversarial strategies for Alice. And each of these strategies essentially involves Alice asking, should I abort the protocol now, or should I send a message and then abort the protocol? And he shows that one strategy of this form must induce a non-negligible bias. And what I want you to take away from this is that you can think of this strategy as computing a deterministic function. Alice looks at the transcript of the protocol so far, along with her internal state, and she just computes whether or not she should abort now or whether she should abort later. And what we observe is that if this coin flipping protocol resists the time-bounded adversary, then this time-bounded adversary must not be able to actually compute this function that tells it whether to abort now or later. Then it would be able to run Cleve's attack, and the protocol wouldn't be secure. So this says exactly that this strategy must be weakly unpredictable. So to turn it into a weak delay function, all we need to do is sort of put it into the correct syntax. So basically, we define setup to be the correct strategy. Sample input simulates the protocol so far up until the round where Alice may or may not abort. And then eval just takes as input Alice's random state in the transcript so far and computes whether or not she should abort. And if the protocol is secure, then this is a weak delay function. OK, but we so far only have the guarantee that the adversary fails with some non-negligible probability in computing the output of this function. And we want to boost this. So a natural attempt is to define a new delay function, which involves evaluating the old one on a bunch of independently sampled inputs, x1 through xl. And now we want to show that this new delay function is, in fact, a strong delay function. And this might look familiar. This is the way that you amplify a weak one-way function into a strong one-way function. And so we want to adapt that proof as well. But there's one problem here, which is that in that proof, the reduction has to know when it's successfully inverted the one-way function. And there it's easy to do this by simply evaluating the one-way function and checking whether it's correct. But in our setting, our reduction can't do this with the delay function, because this would involve computing the delay function, which is too slow. So we need some way to check that an alleged output of the delay function is in fact correct. So we need some verifiability property. But at a first glance, this might seem challenging, because people have tried to construct, say, verifiable delay functions from delay functions, and this requires fancy techniques, like fancy proofs. And so we wanted to avoid that. Instead, what we do is we observe that in our setting, we only care that the depth of the adversary is bounded, but we allow the adversary to have arbitrary polynomial width. So our idea is to use this in transforming a regular delay function into our kind of verifiable delay function. And what we do is we modify the delay function to include not just the output, but also the values of the wires of its circuit on every gate. And so now what the verifier can do is, in parallel, it can check that every gate is correct. And if that's the case, then the output that it yields must be correct as well. And so this is really using the fact that we can take this computation, like spread it out, making it very wide, but not increase the depth. So we're able to do this unconditionally. And one thing that I want to note is we're able to do this unconditionally because this kind of verifiability is much weaker than that required for VDFs. But it is sufficient to get a reduction to go through. And now we can directly apply the proof that goes from weak to strong one-way functions. OK. And the final part of our argument is taking our strong delay function and showing that you can use it to construct a distributed randomness beacon. And our idea is simply to adapt the unicorn protocol. But there's a slight challenge here in that unicorn required a verifiable delay function, which was different in a couple of subtle ways from our delay function. And so we just needed to adapt it for our setting. In particular, VDFs require a uniform input, whereas we had the sample input algorithm, which might not be uniform. And so we just had to do a bit of work here. But it's essentially unicorn. OK. And so I want to finish with some higher level discussion. One question you might be wondering is why we consider bounded depth adversaries as like a formalization of time-bounded adversaries. So if you remember from the unicorn protocol, the reason why it's secure is because there's a bounded time contribution period when everyone must choose the randomness they contribute. And it takes much longer than that to evaluate the delay function. And so formally, people will model this like bounded time computation as having to be done by bounded depth circuits. And the reason why we talk about bounding depth instead of size is that in practice, it's very hard to speed up sequential computation, whereas it's much easier to get more parallel computation. And so like by buying more computers, a powerful adversary can sort of always increase its parallelism, but it's much harder for it to speed up sequential steps. And for this reason, this is sort of the popular way of formalizing time-bounded computation. Another thing you might be wondering is why we're choosing to bound time rather than some other resource. So you might try to require that, say, the adversary has bounded space during the contribution period, but this makes less sense for a couple of reasons. One is that our weak to strong amplification lemma really only holds for bounded depth adversaries rather than bounded space. And the more practical reason is that these protocols like ours in Unicorn, work by requiring that the resource is bounded sort of during the interactive phase of the protocol, but there needs to be more of the resource available after the protocol, right? So the idea is that during the contribution phase, you can't compute the output of the delay function, but to eventually get the beacon output, you must be able to compute the delay function later. And this doesn't make sense for other resources. It's not natural that other resources would suddenly become available as soon as the protocol finishes, whereas for time, you can always get more of it by waiting. And so this is why we called the paper "Good Things Come to Those Who Wait." So with that, I'll just summarize. We showed an equivalence between dishonest majority beacons and a weaker notion of delay functions than verifiable delay functions. And maybe I'll end by saying a little bit about what this implies for practice. So as I mentioned, randomness beacons are very important in blockchains for leader election. And Ethereum actually considered deploying verifiable delay functions, but didn't end up doing it because of basically engineering costs. And so what this work says is that if you really want a dishonest majority tolerant randomness beacon, you need delay functions. And so whether you need to tolerate a dishonest majority is another question, but if you do want to do that, then you need delay functions. And so with that, I'll end. Thanks for listening.
Are there any questions?
Excellent. Thanks for the talk. I have a question which you sort of addressed towards the end, which is, if we're interested in what are the implications of, let's say, bypassing cleave, we know that cleave can be bypassed by changing the model. I think time commitments from the work of Bonena, or am I remembering correctly, tells us that, and so we know from that type of work that time is a way to go there. But in general, it seems reasonable to ask the question, what happens if you have a model, say space-bounded model, you mentioned other resources, or time-bounded model, or there is this party that's going to do something special and such. There are other ways one could generalize these type of observations. Is there any other comment besides the ones that your specific techniques might not apply? You say also something else.
Yeah, so I think for randomness beacons, we haven't seen any actual constructions that come from bounding any resource other than time. So in this way, it's not as well motivated to study bounding other resources. And I think the reason for this is the way that we've seen bounding time is useful is by bounding the amount of the resource that's available during the interactive part of the protocol, but then allowing everyone to have more of that resource after. And so for time, this is easy. You can make the protocol stop after a certain point, and that enforces a time bound for everyone. But it's hard to enforce that everyone has a bounded amount of space, especially in a decentralized setting where you can't see what hardware everyone's using. Someone could easily lie about having more space than they actually have, whereas for time, you can't lie about you can't make your clock run at a different speed than the clock of the universe. So I guess for those reasons, for randomness beacons, I find it hard to see other resources that would be as interesting to study. But maybe for other settings, it would be interesting.
Thanks.
Hi. I wonder something that cleave, you say you circumvent cleave's impossibility. I think cleave still holds because the delay function still, the time is polynomial. And in polynomial time, cleave's impossibility still holds. So I wonder how you can say that you're circumventing cleave. I mean, it takes a lot of time. Maybe it takes 5 hours, 10 hours. But in polynomial time, everything is broken. So it's not really circumventing cleave. You're probably talking about a model in which predicting the randomness too late will be too late, okay? If we care about the randomness for the next block, for the next hour, then we have sequential time and we can deal with it, but it will be broken in 10 hours, but we don't care, nobody cares. Is that a fair characterization that we're not circumventing cleave, but for practicality, we can think of it as effectively circumventing cleave because we can still run these applications?
Not quite. So we do get the property that our beacons are truly unbiasable. So you might be able to predict the value after the protocol ends, but at that point, everyone is supposed to know the value anyway. So our protocols are provably unbiasable, but what we require is that the adversaries have bounded depth. So we define this formally in the paper. The adversaries must have some specific polynomial that bounds their depth. And so the delay function cannot be computed in depth less than the specific polynomial, but it can be computed in polynomial time for a larger polynomial. So you can think of this as some sort of fine-grained model. And really, in this model, you cannot bias the output of the beacon. Yeah.
But cleave talks about polynomial time adversaries, whether they're polynomial depth or it's still polynomial time for any polynomial. This is why
Yes. So our difference is that we require that the adversaries can't run in time more than some specific polynomial. In cleave, the adversaries are allowed to run in any polynomial time. And so that's why we're not contradicting cleave. We're in a different model that's more fine-grained.
Okay, thank you, Miranda. So the next speaker is Nikon. Can you prepare the slides so we can start? So Nikon will talk about the complexity of memory checking with covert security.
All right, thank you, Alon. Today I'll be talking about some joint work with Alette Boyle and Alon Komargodski. The setting we're going to be in today is one of remote cloud storage. So let's say you have some computation that requires a lot of storage or a lot of space, but you don't have or you don't want to use space, or you don't have space to do it yourself locally. There are many examples you could think of, like file storage and more, and a common solution to this paradigm is to use a remote cloud server as a storage mechanism. So maybe there's something like this. We have a user that has some access to data, and the user is going to make a bunch of requests to some server. And throughout this talk, we're going to think of the server as like a passive storage mechanism and not one that does some active computation. So the user could issue read or write requests. Like here, it's writing data to index or address 3. It could write some different data prime to address 8. It could issue a read request to the third address to get data, and that's what should happen. And you can rewrite data like double prime at address 3 and so on. So you can overwrite values. But this naturally motivates a few questions of trust on the server. Like, what if the server is adversarial? The first is a basic privacy concern that, okay, you're sending your data to an external cloud. That seems bad. Thankfully, standard secret key encryption directly solves this. Or if you want something information theoretic in some split server model, you could do secret sharing. Perhaps more a subtle or privacy concern is access pattern leakage. The server can learn where you want to access, and this can really be influential in practice. And so oblivious RAM is the solution to exactly this privacy concern, which was introduced by Goldreich and Ostrovsky. What we're going to focus on in this work is the integrity trust concern. It's one where if the server becomes malicious or active and tries to change the outputs that it sends you, it may modify your data. And and ideally, we'd like to make sure that all the responses sent back to the user are going to be correct. And you can imagine combinations of privacy and integrity as well, but we're not going to talk about them today. So can we prevent the adversary from just arbitrarily modifying data, say deleting your data? Unfortunately, no, you can't. If you don't have a lot of space yourself and the server does, it could just delete your data. You can't stop that from happening. But what you could hopefully stop from happening is having the server undetectably change your data. So maybe you can notice if the server was to tamper with your data. And so this is something we can reasonably hope for. And the name for such an object is called a memory checker. Yeah, so memory checker is a protocol that prevents adversaries from undetectably modifying cloud data. And this was introduced by Blum, Evans, Gamel, Conan, and Nauer. And to sort of visualize it in our previous picture, we're going to think of the memory checker, or an MC, as some intermediate object, like a compiler, that takes in user read or write requests, compiles it to a bunch of like query hats that could also be read or write. Maybe there's a bunch of queries sent back and forth. And then the memory checker is supposed to give some response back to the user. And the user can issue this many times in an online way. And just for the sake of notation, I'm going to call the queries between the user and the memory checker logical queries. And I'm going to call these query hats physical queries that the memory checker issues to the server. And I'm also going to make a read-only reads assumption in this work, where every read query that's logical is only going to induce physical read queries. So like if you're doing a read, there should be no reason, ideally, that you're changing the server in some way. But this is going to be an assumption in our work. And there are two natural conditions you'd have for a memory checker. One is completeness, which is sort of the obvious one, which is that if the server were to behave honestly and just store your data, the memory checker should give some response that's the correct RAM response for the corresponding read. The more interesting notion is a soundness notion, which says that if the server, let's say, is computationally bounded, then the probability that the memory checker gives an incorrect response should be low. But of course, we can't, the adversary could just always zero everything out, so we're going to give the memory checker an option to send out like a flag or an abort signal. So we want to make sure that you're always either giving a correct response or aborting. And the probability where neither of these is true, in other words, you're sending an incorrect response to the user, is the probability P that we call the soundness error. And like a natural application here is one of, let's say, storing your files on some cloud. The user would run a memory checker locally. This should be some small space thing. They use the memory checker to interact with some server that's potentially corrupted. And by the guarantees of the memory checker, you're guaranteed correct responses, or if not, you'll detect it, and you can complain about your cloud storage provider. There's some related applications that I'm not going to get into for the sake of time, like secure hardware enclaves, provable data possession, retrievability systems. And there's an offline notion of memory checking that's been quite useful in some recent snark literature, which is a version of memory checking, but all the queries sort of are given at the same time, and you're only asked one correctness condition, as whether everything was computed correctly or not. And accumulation schemes as well is another one. So ideally, we'd like these memory checkers to be efficient, but what are the notions of efficiency that we mean? I'm going to focus on two main complexity measures. One is the amount of local space, like trusted private local space that a memory checker can store locally. And this better be sublinear in the number of entries that you want to store in the first place. Otherwise, there's a trivial solution of just storing the full data locally, but that's not so interesting. So for the rest of the talk, I'm going to assume the space is at most n to the 1 minus epsilon for an arbitrarily small constant epsilon. And this RAM icon is going to denote the local space contents, so the local state of the memory checker. And the second and more relevant notion of efficiency is the query complexity, or the overhead. And this is the number of physical queries made from the memory checker to the server for each underlying logical query from the user. And this is the quantity we really want to minimize. So you can ask, what do we know? What constructions do we have? What lower bounds do we have? Etc. So in the case we want statistical soundness, meaning we want soundness even against servers that are computationally unbounded, there's an upper bound of n to the epsilon in terms of query complexity, where the local space is n to the 1 minus epsilon. And in fact, there's a matching lower bound, showing that this is tight up to constant factors. And more generally, you can have any trade-off between space and query complexity as long as their product is n. Okay, on the computational side, though, the story looks a lot more promising efficiency-wise. If you just do a standard Merkle tree, this will give you an upper bound of log n, Roughly speaking, what you're going to do is store the root of the Merkle tree locally, store the full Merkle tree in the public data, and then every logical query, you're going to look at a full path from a root to a leaf. And that's why it incurs a log n overhead. It turns out that you can optimize this to log n over log n by some nice tricks that Papamantu and Tomasia showed. There was also a corresponding lower bound of log n over log n, suggesting that this is a tight picture. But there are a couple of shortcomings of these lower bounds that I'm going to talk about on the next slide, and this will be the focus of this talk, is this lower bound in the computational regime. Okay, so what are the limitations? In the work by Dwork, Nauer, Rothblum, and Vaikunthanathan, their lower bound only applies to memory checkers that are both deterministic and non-adaptive. And we view this as a big restriction. Roughly speaking, it says that for every logical user to every query to an index I, the places that it looks up, the locations that it looks up in physical memory are fixed and depend only on I. So they can't be randomized in any way, and they can't change adaptively throughout the computation. On the other hand, in some previous work we had last year, the lower bound only applies if the memory checker is sufficiently strong in terms of soundness. So roughly like an inverse polynomial soundness guarantee has to hold before the memory checker says anything. And it doesn't rule out potential memory checkers that have like a larger soundness error. And this soundness error is what we're going to focus on in the context of covert security. So in many settings, as introduced by Aumann and Lindell, so in many settings, like commercial, political, or social, malicious adversaries have some incentive to not get caught. And negligible soundness here can often be overkill. You know, if you detect an adversary with 90% probability, is it really that much different from detecting it with 100 minus negligible percent probability? Maybe the malicious adversary, 90% is enough of a disincentive to stop them from doing whatever they were going to do. And in fact, this relaxation from 100 minus negligible to 90% has enabled asymptotic efficiency gains in various metrics and various multi-party computation protocols. And this covert security question makes sense in the memory checking setting. Let's say you're some cloud server provider. You don't want to have a bad reputation of getting caught, and 90% is probably going to be too high of a risk to pay. The main question we ask in this work is whether this lower bound can apply to memory checkers that have this relaxed covert security notion. So can it have query complexity that's like less than log n over log n, or even constant? Right? Like concretely, is there a memory checker that has only a 5% soundness error, meaning you can catch it 95% of the time, and query complexity like 2, even as n gets large, right? If this object were to exist, I would imagine it could be extremely useful in many settings. And our main result is that essentially you can't do better with covert security. So every memory checker, even if you allow the soundness error to be in any constant, must have a query complexity at least log n over log n. And this is, once again, tight up to constant factors by Papamantu and Tomasia. It's unconditional, so there's no crypto assumptions or anything, and it holds even like in a random oracle model. And unlike the Dwork et al. Results, it's going to handle randomized and adaptive memory checkers as well. And one quick interpretation of this result is that unlike many other functionalities in MPC, covert security does not enable efficiency gains for memory checking. Let me give a very brief technical overview. So our approach is to, it very much follows the previous work of using a memory checker that's too efficient to compress random bits of information, which is impossible. And it'll use something like this. If you're to transmit a uniformly random subset of size k out of n from Alice to Bob, it should need log of n choose k bits of randomness, even if there's some shared randomness between Alice and Bob. So here's a very quick sketch of the protocol. So Alice and Bob are going to share some randomness in the form of an initial public database, DB0, and some initial local state of a memory checker. Alice, knowing this set S, is going to write a 1 index into the memory checker for every index in the set. And this is going to correspond with some updates to the public database, let's say here. And so it's going to give some updated database DB1 and some local state ST1. The memory checker is then going to just send the updated state over to Bob, who will then try to do a recovery procedure by reading every single index I into the memory checker. And then it will do it on, well, okay, ideally it would do it on the updated database DB1, but unfortunately it doesn't have this information. It only has the DB0 that's shared in the public randomness. And so this corresponds to some form of an attack on the server. And we know from the soundness guarantee that if the memory checker tells you either 0 or 1, that should correspond with probability like roughly 1 minus p to whether exactly whether the I is in the set S. This is what Alice wants to communicate. But of course, the memory checker has the option to abort. It might notice that there's some issue with the database, and here we can't really conclude anything meaningful if this happens. So the key idea in this previous work is to partition the server's memory into a heavy, medium, and a light set that I won't really get into for technical reasons, but roughly it corresponds to analyzing like the heavy hitters of the distribution where you look at a random index I and you look at the locations that it reads. And then with these like heavy, medium, and light decomposition in mind, we can have the previous picture and have Alice also send over the heavy set and the updated database. And this has the benefit that will usually prevent this like flag case that comes up because the relevant coordinates are probably going to be updated, and so the memory checker won't notice that there's going to be any issue. That's the idea. But there's an issue of computing this partition, which is that to actually get the soundness guarantee to go through, we need this partition computation to be efficient to invoke soundness of the memory checker. And the previous approach was just to guess. Like all we needed is for Q queries to correctly guess. And so there's going to be some 2 to the Q factor security loss, which is going to be way too big for our setting. And so we need to overcome this somehow. It may not be immediately obvious how to do this, because like the heavy set could depend on internal local state of the memory checker, which might change. And it could adaptively change as things go on. So our idea, in a very quick nutshell, is to efficiently learn an approximation H by making many additional dummy read queries at a particular point in time. By read-only reads property, if you make many read requests, nothing is going to change. So you can just make many read requests, like polynomially many, in fact. And then by the right multiplicative and additive turn-off bounds, you can learn an approximation of the heavy set efficiently that makes the lower bound argument go through. I'll skip the summary slide for time, and I'll leave it with some open questions. So is there a more general framework that we can have to understand whether relaxing covert security can enable efficiency gains or not? Like, why is memory checking different? That's not super clear to me. And is there any way technically to avoid this like read-only reads assumption? All right, that's all. Thank you.
Time for one quick question. I have a question. Do
Okay.
you need perfect completeness?
No, so yeah, we work with constant completeness as well. The lower bound goes through, you just need some gap between the soundness and completeness.
Okay. Go for it.
Yeah, could you just say like one more thing about like the reasonableness of this read-only reads assumption? Like, are like other?
Yeah, all the constructions that are like not contrived that I know of satisfy this. You can change this like without lots of generality. You can make some version of this assumption, but that will change to like a weird soundness definition that we don't view as too natural. And so that's why you can't like formally get rid of it. But yeah, that's a good question.
Thank you, Nico, again. The next speaker and the last of this session is EZ. He will talk about fine-grained complexity in a world without cryptography.
Okay, thank you. So I will talk about our work, fine-grained complexity in a world without cryptography. This is a joint work with my co-advisors, Josh, who is not here, and Kevin, who is here. Oh, sorry. Okay. So I'll first talk about our motivation and then explain our results. So in my talk, I will keep things high level. So our work is about some relation between cryptography and fine-grained complexity. But our motivation actually comes from fine-grained cryptography. But before talking about what fine-grained cryptography is, let's first see what we have in like the Euro sense of cryptography. So usually in cryptography, we have protocols that run in some polynomial time, and we require they are secure against adversaries that can run in any polynomial time. We know such cryptography can be built from a wide range of assumptions, including one-way functions, number theory problems, lattice problems, and many other things. But on the other hand, we also require these assumptions to build cryptography because, anyway, at least this cryptography, except for very few examples such as secret sharing, they at least imply one-way function. So a natural question to ask is, what if we live in a world without one-way function, and these assumptions are all false? Or more extremely, what if we live in a world where P equals NP? And this is why people study fine-grained cryptography. So in fine-grained cryptography, our protocol still runs in polynomial time. But for security, instead of requiring security against adversaries running in any polynomial time, here we only require it secure against adversaries that runs in some specific polynomial time. Like, as long as the exponent in the security is bigger than the running time, then we are good. So for example, if we have a very big gap between C and D here, then we can hope that this still give us some useful cryptography that we can use in practice. And the hope here is that it might be still possible to construct fine-grained cryptography even if P equals NP. However, to construct fine-grained cryptography, we still need security against we still need some security assumptions, computationally lower bound assumptions, because we don't have such assumptions unconditionally. And here, we will draw these assumptions from a field called fine-grained complexity conveniently. So what is fine-grained complexity? Basically, it studies hardness of problems in P. So many problems are known to have, for example, a quadratic time algorithm, but they are not known to have sub-quadratic time algorithms. And people use fine-grained reductions between these problems to study relations of hardness between these different problems. This is much like how we use polynomial time reductions to study relations between NP problems. For example, one problem we study a lot extensively in fine-grained complexity is called K-sum. This problem is given K list of integers modulo some m, and we want to find one integer from each list so that they sum to 0. For example, this is an instance of 3-sum problem modulo 29. And this is a solution to it. So it is known that there is an n to the k over 2 time algorithm for this, and this algorithm is not quite hard. However, even if this problem is extensively studied, it is still not known that, there's still no better algorithms known for it. So people make this K-sum conjecture, which says K-sum cannot be solved in better than n to the k over 2 time. Recently, people also start to study average case version of this problem. And except for in some parameter regimes, there is no better than n to the k over 2 time algorithm for the average case version of K-sum. So people also make this average case K-sum conjecture, which says that even in average case, K-sum cannot be solved in better than n to the k over 2 time. Okay, so now we see, so I want to just mention that K-sum conjecture is actually used a lot in fine-grained complexity. So we have seen assumptions from fine-grained complexity, and what fine-grained crypto can we construct from this? So it is known that from average case fine-grained assumptions, such as k-sum, we are able to construct fine-grained versions of one-way functions and key exchange. There are also many other works on this, such as construction of proof of work from fine-grained assumptions. Okay, so to summarize, now we know that now we see that even if there is no Eurocryptography, we could still hope for some version of fine-grained cryptography that is useful. And in addition, there are known constructions of fine-grained cryptography based on fine-grained assumptions. So this leads to our main question, which asks, what will happen to fine-grained assumptions, or in general, fine-grained complexity, if there is no Eurocryptography? And we show two results in this direction. So first, we show that if there is no one-way function, then the average case k-sum conjecture we just talked about is actually false. And second, we show there will be faster discrete log algorithms if and only if we can show certain fine-grained reductions. Okay, so then I'll elaborate more on these results. Yeah, so the first result says if there's no one function, the average k-sum conjecture is false. So this actually holds for other fine-grained problems that have a planting algorithm for it. For example, 0k-click. So I will not elaborate much on planting algorithm, but roughly speaking, it's an algorithm that generates a yes instance of k-sum with a specified solution. And this algorithm is actually one of the main components of our proof. And it's also used in prior works. Okay, so what does this theorem imply for us for fine-grained cryptography? It will say, it means if there's no one-way function, then no fine-grained cryptography constructions will have some limitations in security. For example, the previous construction of fine-grained one-way functions I just mentioned will not be secure against n to the c time adversary for some constant c, because that construction is based on the average k-sum conjecture. Also, I want to say that I think the contrapositive of this result is also very interesting. So the contrapositive says, if average case k-sum requires n to an exponent that is super constant in k time, then we know one-way function exists. And actually, average case k-sum is conjectured to require n to the k over 2 time. So this is an example of basing the Eurocryptography on fine-grained complexity problems. And to our knowledge, this is the first known example of such kind. Okay, I'll now talk about the second result. So the second result is about fine-grained reductions. And recall that fine-grained complexity is mainly about studying fine-grained reductions. And what our result says is cryptography can give a barrier to such fine-grained reductions. But to state our results, I need to define a new problem called k-sig. K-sig is a problem with the same structure as k-sum, but over a different underlying group. So it's essentially still given k lists, and we want to find k elements, one in each list, so that these elements, the product of these elements is 1 in a cyclic group G. And this can be viewed as a generalization of k-sum, as you can choose G to just be the integer modulo m group. So this, you can see that this the k-sig problem has the same structure as k-sum, or even you you may view like it's just syntactically almost the same, but it's actually unclear if they have the same hardness. So actually, what we are able to show is that the following two are equivalent. Like if there is a fine-grained reduction from k-sig over group G to k-sum in time less than square root of size of G, then the discrete log over G has a faster algorithm than the general algorithm, which takes square root G time. And the other direction is also true. So what does this mean? So first, this presents a barrier for reducing the k-sig problem over group G to k-sum. If G is a group that you believe in which you believe discrete log does not have a better algorithm than the general algorithm. For example, you can take G to be your favorite elliptic curve group. Also, in the other direction, this means that if you can show some fine-grained equivalence between the k-sig problem and k-sum, it will give you faster than known discrete log algorithms. So in high level, this means like advance in fine-grained complexity could actually give you some advance in maybe like cryptanalysis. Yeah, and in general, this tells us that for k-sum-like problems, the underlying group structure seems essential for understanding the hardness. So it's not like what's the first impression might give you that like the group structure does not matter, and because the k-sum and k-sig have the same structure. Okay, and I'll now talk about some open questions. So first, the obvious open question is, can we further generalize these results? For example, can we show more conjectures that are false if we assume there are no one-way functions? This is equivalently as saying, can we show more conjectures that will imply existence of one-way functions? And also, can we show more barriers to fine-grained reductions using cryptography? And I want to mention another open question. So in our result, we show that if one-way function does not exist, then k-sum conjecture will be false for sufficiently large k. However, it doesn't give you anything for a specific k, for example, k equals 3. But on the other hand, if you know k-sum can be solved faster for a very large k, it is reasonable or even plausible to think that it will imply some maybe slightly faster algorithm for 3-sum. For example, one concrete version of this question is, suppose you can solve k-sum in n squared time for all k. Does that mean that you can solve 3-sum in like n to the 1.99 time? So this might seem plausible, but actually we think it's very difficult, a very difficult problem, and might be beyond like current approach of fine-grained complexity. Yeah, but we encourage you to think about it. Thank you, that's the end.
Thank you. These are very interesting set of results. I have a comment and a question, and bundled together, really.
Okay.
So there is another set of flavor or family of fine-grained cryptography, which is not so related to total time spent by the adversary, but it is with bounded depth.
Like circuits? You mean like bounded depth circuits? Or
Do you say poly?
Sorry, I mean, do you mean bounded depth circuits?
Correct.
Yeah.
Yes. So, for example, and that's interesting because you sort of, the usual case to motivate fine-grained crypto is, suppose that there's no one-way functions, then we can use this. Your work seems to sort of introduce some care into that assumption. However, there are some results for fine-grained constructions. For example, there are symmetric key and private key encryption schemes that are secure against acid zero adversaries.
Yeah,
so
yeah.
on the depth, and that's true unconditionally. So those are going to be fine.
Right.
The question I had was there's another set of results on one depth that's based on an assumption that's related to assume the log space is different than NC1. Really,
Right.
it's not exactly this. And then we're able to build more public key encryption and such. You don't mention this, but do you see, have you looked into that? Do you know what one-way function existence, failure of existence would imply for that type of complexity?
Yeah. So I know. I think. We've seen like those line of work before. Like, I think it's, if I remember correctly, it's like you can build like one-way function or PRG, something like that, in like maybe NC0, and you can prove like it's unconditional secure against maybe AC0 security or something like that. Yeah, I think that's kind of like independent with our result, and somehow we all call this fine-grained version of crypto, but I think they are like different things. Yeah. But
okay. And if anyone in the room knows, come to me. I'm curious about this topic too.
sorry. Okay.
No, I'm opening the question to everybody.
Okay. Yeah, thank you for the question.
Yeah, very interesting. I think I misunderstood something fundamental. The K-sum conjecture, or how do you define a fine-grained conjecture? Because it looked like it's exponential in K. So what is, like, why do we call this a fine-grained conjecture versus like an...
Yeah, I see. So I think we call this fine-grained conjecture because like if you fix a constant K, then like the hardness you assume for it would be a like polynomial instead of like exponential. So here the K, we always view K as a constant instead of something that depends on n.
Okay, but I guess in your, what you're saying is if I make K of lambda, then I can construct one-way functions from it. Right?
Yes, yeah, so like it's saying that if like that like average case K-sum conjecture holds for all constant K, then we have one-way function. Yeah,
but
so
your statements are about then asymptotic in K, no? Or like for big enough K.
Oh, I see. You mean that thing? Okay. How can I go back? This one you mean?
Yeah, for example.
Okay. So I think you can also. Okay. Okay. So. Oh, I think. Sorry. Let me think of a good way to explain this.
We can also take it offline.
Or maybe we can discuss it offline.
Thank you very much.
Does it work? Yes. Yeah, okay. So you have this result that says if K-sum is hard enough, then one-way functions exist, right?
Right.
Is that constructive? Does this give me a candidate one-way function?
Yeah, it is constructive.
So I get like basically a candidate one-way function from K-sum.
Right. Yeah.
Yeah, nice.
Thank you.
Any more questions? Let's thank all the speakers of the session again.